Hi, and welcome to episode 5 of Astromagnet. I'm Arush Ramadurai,
And I'm Ishan Chakravarti.
and today we're excited to be talking to Bertrand Halperin. His research concerns condensed matter physics, and he served as the Hollis Professor of Mathematics and Natural Philosophy at Harvard.
Welcome to the podcast, Professor Halperin.
Well, thank you. It's really a pleasure to be here. I'm flattered that you invited me, and I'm happy to tell you what I can.
So to start off, when did you decide to become a physicist?
Well, I think I really decided that at the end of my freshman year in college. Before that, I was sort of undecided. I was thinking of medicine, going into medicine, possibly going into physics. But I really liked my physics courses, and I didn't so much like the organic chemistry course that I took. And I thought, well, I might not do so well in medical school. I better go into physics. And,
so were there?
But I did well before that. I had. If I go back earlier, when I was considering other possibilities, but I was always interested in mathematics as a kid, and physics and science, and my talents were on the mathematical side. So physics was logical, but I didn't really want to do pure mathematics. I thought something a little bit more applied would be more interesting to me. So that's why by the time I got to college, I kind of had physics and medicine also appealed to me as a possibility. But that's how I got into it.
So among those courses that you were talking about, were there any courses like specifically or experiences or teachers that you felt, cemented that for you, or were some kind of realization for you?
Good question. Well, I think the first course I had in physics at Harvard as an undergraduate was, I had some advanced placement, so it was sort of like the third term of physics. Let's see. No, actually, I'm sorry, it was the second term of physics, but it was taken in I took it my first term, and it was they had a specially enriched section, and there was a very good section leader, and that really did kind of cement my feeling that I did well in the course, and that it was good for me. It's not that if I think I wouldn't say, if I look back on all the courses I had in physics, that wouldn't be the one that most stood out. I would say the one that, if you wish, perhaps you could say most cemented me into physics, but I was already in physics. But the course that stood out most in my undergraduate years was a course in, it was the first first year introductory course in quantum mechanics that I thought was really very exciting. And I was also interested, there were some math courses that I also really liked as an undergraduate, but those were sort of the courses that stood out.
So what made you decide to study condensed matter physics as opposed to like other fields?
Yeah, so that I got into it through a summer internship I had in 1961, quite a while ago, but after having 3 years of college, but I had advanced standing, so I essentially had finished my undergraduate work. But I had a summer internship at Los Alamos Laboratory in New Mexico, and they assigned me to work with some people who were doing experiments scattering neutrons from aluminum. So they had a reactor there deep in some canyon, and they used it originally for weapons purposes, but then they had these. They were also using it for basic research, and the idea. This was brand new at the time, only a couple of years old. They found that by scattering neutrons off materials, under appropriate conditions, you could learn a lot about the vibrational spectrum of the materials. So you have, a lump of aluminum has, gazillion atoms, and you can think of them as sort of connected together by springs, and they can vibrate. And there are many different vibrational modes. If there are 1 million atoms, there are 3 million different vibrational modes. They can move in every direction. But there's an order to them. They're not just random vibrations. You can characterize them by a wavelength, that you have modes that they're like sound waves that have a mode and a frequency, but the sound waves, they go up to very short wavelengths and frequencies that are far, far higher than anything you can hear. And you can map the frequency versus wavelength out using neutron scattering. And that tells you something about what the forces are between the atoms and so forth. And this was new at the time. I knew nothing about solids, or I didn't really know much physics. I did know some quantum mechanics. And they gave me a book by Leon Brillouin to read about basically the properties of electrons and vibrations in solids, that is periodic solids, meaning crystals, where you have a periodic array. And something that I thought would be exceedingly complicated had some really beautiful simplifications in it. And that kind of hooked me. I thought this was really beautiful. And that's what caused me to really get involved, to get interested in it. And then I learned about superconductivity. I learned about other things after that made me realize that it was really a very interesting field. But that was what got my interest in it.
So what areas of condensed matter physics do you study, and what questions does your field try to answer?
Yeah, so first of all, I should probably, not everyone knows what condensed matter physics is. In fact, I'm not even quite sure. It's a broad subject with very ill-defined boundaries, and I have over the years been involved in various aspects of it. Condensed matter means that it's looking at material. It's really materials that could be either solids or liquids, but they're materials. We have many atoms that are close enough together so the atoms, the interaction between the atoms are very important. So you would probably exclude a gas where the atoms are basically moving independently. I'm also not interested in things that happen at extremely high energies, like in a high energy accelerator, but these would be things that are usually, they might be at room temperature, or actually a lot of the things I'm interested in are very cold. They'd be in very cold refrigerators. And they could be solids, liquids, they could be metals, insulators, superconductors, magnets, liquid crystals, and even now they're systems they're very dilute systems of atoms, but they're trapped at such low temperatures that the interactions between them are important, and quantum mechanics can be important. So that's the general field. And over the years, I've been interested in my early work. A lot of it was in statistical properties of materials, the kind of phase transitions between them. In more recent years, I've focused on electronic properties, typically at low temperatures, often in very strong magnetic fields, often in devices that are very small, so that the confinement, because the device is so small, the electrons in them behave in a different way than they would in just a big lump of the same material. And there are some very fascinating things that happen, particularly at low temperatures, strong magnetic fields. And these are all things, what I've been, again, in recent years, almost everything I am interested in is, or have focused on, not that I'm interested in many things, but my work has focused on things that involve quantum mechanics. That is, the conditions where the laws of motion have to be understood in terms of quantum mechanics, that classical laws are really quite inadequate. And so some very surprising things happen, or non-intuitive things happen. They're not intuitive until you develop maybe an intuition for the quantum mechanics, but they're very, some things have been very surprising, and that has been the focus of my work in recent years.
So it sounds like you could have a lot of real world applications, especially since you deal with things at like room temperature or really cold temperatures. So would you be able to speak on that?
Right. So I would say that very little, if anything, that I've done has a real world application. I have to say that I think the field as a whole certainly does, because it is the basic physics that underlies devices of various kinds, materials. So, things, the field includes, of course, trying to build better superconductors, that better materials that have better interfaces with biological systems, various sensors that you could use in biological systems, or for detecting pollutants, or for in energy conversion. All of those things involve condensed matter physics at one level or another, including surface physics. But my own work hasn't been particularly motivated by devices that are, and a lot of what I've done, because it's at such low temperatures, it's very expensive to get to low temperatures, or large magnetic fields are very expensive. So they are not, at the present, most of the things I've been interested in don't have any immediate commercial applications. They may have applications in the laboratory as ways of finding out, the experimental. Certainly everything I do, almost everything I do, is tied to experimental work, to people who do experiments on real materials. I am mostly interested in that, but they're trying to find out fundamental properties, which maybe 10 years, 20 years, 30 years in future will actually have some very surprising impact, or maybe these particular materials won't, but things we learn from them might. So I think there is, justification for supporting it from a commercial, for the field. But my role is sort of to kind of provide the basic knowledge that will help other people develop somewhat less basic knowledge and more practical knowledge. And I hope that, and also to train students who might go on with having the basic knowledge, they'll be in a better position to go on and do practical things. So I have that hope, but I have to admit that my own motivation has really been curiosity. I want to understand how the world works, and that's what's driven me. I can't claim, for better or for worse, I've not been especially goal-oriented in the sense of trying to solve practical problems, but fortunately many other people are.
So what other research experiences, such as your thesis work, have you enjoyed?
Well, so actually I did enjoy this work at Los Alamos Laboratory, which was not part of my thesis at all. It's hard to point to any one thing. In general, what I enjoy is what gives me the most pleasure is when I work hard and sweat on a problem, and then it seems like I can't solve it, and then suddenly, or maybe you see a way of solving it. Then sometimes it turns out that's wrong, but then you go on, and then when eventually you've gotten to the point where you really have concluded that you've solved the problem that you thought was hard, and maybe it was a problem that no one else in the world knew the answer to. Maybe they hadn't thought of it, the problem in the first place, but that you sort of see some light in this amazing universe, that you see some little aspect of it that you're seeing maybe for the first time, and that's very exciting. And so that's happened in numerous cases, not necessarily anything that anyone else considers important, something that I was interested in. And when you solve it, that's exciting. So I don't know, my thesis, yes, I did have, there was a problem. My thesis advisor gave me a problem which I couldn't solve. And he said, well, maybe you could solve it in one dimension. You couldn't solve it in three dimensions, maybe you could solve a certain problem in one dimension. it turned out that, I mean, he didn't know how to solve it himself, but he thought maybe it could be done because a lot of problems could be. And I worked very hard. It turned out to be much harder than I thought, and that I think that he thought. And I managed to find a rather elegant solution to it. I don't know how important it was, but at least it was exciting. And that was my first real accomplishment in, doing something that I really thought was original that no one else had done. And that was, that was certainly exciting. And then I did other things in my thesis that were also, it turned out that someone in Russia did it ahead of me, or not exactly the same thing, but had done somewhat similar things, but it hadn't reached the US yet. So those were two early things. And then there have been various occasions when I've either had an insight or managed to sometimes not necessarily solve a problem, but put a few things together in a way that made them all hold together and could write a coherent explanation of what was going on, or hypothesis about what was going on that other people could take notice of. And that's all, those things were very, those were the high points, and there've been just many different ones. And I should say that sometimes some of the things I thought were important have turned out not to be important, and other things I thought weren't of any great importance that turned out that they were more important. So in retrospect, I should have appreciated them more, but didn't.
Well, one of the things you're known for is helping to predict this thing called the hexatic phase.
Yes.
So could you explain what that is?
Okay, let me try to explain that. So first of all, this is not quantum mechanical at all. This is purely a non-quantum mechanical, what we call classical statistical physics. And so this phase called the hexatic phase, which I worked on particularly with David Nelson, whom I think you may have already interviewed as well, we were interested in 2 dimensions. It turns out that it actually can exist in 3 as well. And we were interested in the problem of how a 2-dimensional crystal can melt. In 2 dimensions, well, it doesn't mean that it's that it's fiction, but you can have, say, atoms on the surface of, or let's say electrons on the surface of liquid helium. The electrons are trapped there and they form, at low temperatures, they'll form a crystal, actually a 2-dimensional crystal. And if you heat it up, that crystal will melt. And there are, the crystal typically of 2 dimensions, they're hexagonal or triangular crystals. This looks like a honeycomb, like the centers of a honeycomb lattice rather than a square lattice. And so you have this very ordered array. And of course, at high temperatures, the liquid, so the atoms are moving all over the place, and there doesn't seem to be any long range order. There may be short range order in that every atom is surrounded on average by 6 others, but sometimes it's 7 and sometimes it's 5. And we were trying to understand how you describe that process. And what we decided was that, at least under certain conditions, the melting would happen in 2 stages. First, you'd lose what we call the translational order, and second, the what I'd call the orientational order. So it's a little harder to explain in terms of a triangular lattice, but think about a square lattice. Suppose the atoms, for some reason, were arranged in a square lattice. So it's like if you have a sheet of graph paper, and the atoms were arranged at the corners of the graph paper, but they might vibrate a little bit about it. But still, even though they're vibrating about it, you have this long range order. So let's say the graph paper has a ruling of 1 millimeter, let's say. So if you have an atom here, that's some atom here, and I go 100 millimeters away along one of the lines, I'm going to have a high probability of finding an atom. If I went 101, I'd find an atom, 102. But if I went 102.5, I wouldn't find an atom, because they're in a periodic array, like on this graph paper. So I don't know if this can be seen. So whoops, I'm trying to hold it horizontally. So we have these lines and they're really regularly arrayed. And then I could also have horizontal lines as well. Now that's a crystal sort of, because it has this long range order. And it's two things, both the spacing is regular. And of course, there's a difference between a vertical and horizontal is different from say 45 degrees. So there's an orientational order. Now, suppose I tore this up into little pieces and I put them back together in such a way that the pieces were completely random oriented and everything. That would be like a liquid. But now suppose I put them back in such a way that the spacing was, I put one here and one here and one here, but I always put them so that they were arranged with the lines vertically and horizontally. So then it would have orientational order. So if I had an atom here, it wouldn't tell me that I had an atom here. But if I had a bond pointing up here, it would tell me that there's also a bond here, and there's not much likely to be a bond here. And with the honeycomb, it's a six-fold order, that there are six directions where the bonds can be, and at 30 degrees away from them, it's unlikely to have a bond. So this was the hypothesis, the assumption that you could have a phase that was intermediate between a solid and a liquid. So it didn't have any of this long-range translational order, but still the bonds would be arranged either vertically or 60, well, yeah, this would be 60 degrees away from them or 120 degrees away from them, but it would favor certain directions. And that's what we because there were six directions, that's hex. And there'd already been there's something more common called the nematic phase, in which it has two directions picked out. So the atoms they're randomly located, but they're all pointing sort of, they're typically rod-like molecules that are pointing in one direction. Well, they're obviously left and right are equivalent for these atoms, but they're different from vertical. That's called nematic. So we coined the phrase hexatic to be something like a nematic, but with six-fold order rather than just two-fold order.
So it's basically about like electron crystals melting.
So actually, we weren't interested in electron crystals particularly, but it could be an electron crystal that melts, but it could be, there are other realizations of it. So it could be atoms weakly adsorbed on a surface, or liquids. So some of the realizations that have experimentally seemed to show this kind of order were little, they're artificial materials, if you wish, made of colloids, which are very tiny particles, say micron-sized particles in a fluid suspended. Let's say you have two glass plates, so you have a thin layer of fluids, and the colloids, they may have charges, so they repel each other. They try to form a solid, but if you increase the density of them, or you change the temperature, the solid will melt, and it does have a phase that's intermediate. And there are also three-dimensional liquid crystals that have something equivalent to a nematic phase. These are basically they're layered materials actually. So the molecules occur in layers. Of course, not at very high temperatures. At low temperatures, they form a solid, but there's an intermediate temperature phase in which they form layers where the atoms within a layer are just randomly oriented. And then if you cool it, before you get to the solid phase, there's actually a phase in which the atoms form this kind of hexatic network that within any given layer, let's say, the bonds tend to be oriented. The atoms are kind of randomly located in space, but the bonds between them tend to be oriented in six directions, and that's the same in every layer actually. So you get this thing where there's order, there's translational order in the perpendicular direction, z direction, because they're layers. But within a layer, there's not this translational order, but there's this six-fold broken symmetry or six-fold order, six-fold anisotropy within the planes of these layers. And of course, the planes of the layers are different from the vertical direction anyway. but that's the three-dimensional hexatic phase. So there are no, as far as I know, the electron. So as far as I know, no one has ever observed or even figured out a good way of seeing a hexatic phase in the melting electron. I gave that as an example of. So people have seen them. There are beautiful experiments that show the phase transition in these electrons on the surface of helium, but not with the kind of resolution or with a kind of measurement that would tell you whether there was a hexatic order above that transition.
So a lot of your later research has been focused on quantum Hall effects. So what
Right.
are they, and why did you study them?
Okay, so quantum Hall effect was actually first discovered experimentally. Well, there was some hints of it in the 1970s, theoretically, but the experiment that really set off the field happened in 1980. It was von Klitzing, Dorda, and Pepper did the measurement, and it's what they were looking at is well, all of these quantum Hall effects, they take place in what we call two-dimensional electron systems in strong magnetic fields at low temperatures. And two-dimensional electron systems, again, they're real. These are not electrons on the surface of helium. They are not in the right density range. But these are, in this case, they were looking at actually electrons trapped at an interface between silicon and silicon dioxide. Actually, it's really a transit. That's what transistors are really. Electrons are really in these two-dimensional. They're trapped in a two-dimensional layer between a semiconductor, in this case, a semiconductor and insulator. But a lot of experiments are done where the electrons are trapped in a narrow layer between two different semiconductors, and they're trapped in such a way that the motion perpendicular to the layer is really completely frozen out in quantum mechanics. If you confine something too much, the energy it has a discrete set of energy levels, like in an atom, and those energy levels could be very high. So everything gets frozen out into the lowest possible quantum mechanical state in motion perpendicular to the layer. But it's still free to move within the layer, completely free to move within the layer. And that's a two-dimensional electron system. And now it turns out that one of the things you can study in these two-dimensional electron systems is their electrical properties. You can attach wires to the two-dimensional electron systems. You can put a current through the two-dimensional electron system. And then on the edges of the system, you have contacts and you can measure voltage differences. So the usual thing you do is you would measure a voltage drop along the direction of the current. So if the current's flowing through, you have some kind of a bar, a rectangle, let's say, and let's say it's like in this screen, the current is injected, let's say, on one side, and it comes out on. It's hard because this is all backwards here. It comes out on the other side, so it's moving in the X direction. And then you could attach two contacts on the bottom here. That would be, let's see, this one here. I can't, oops. Here we go. We have two contacts on the bottom, and I can measure the voltage drop along that. That's in the X direction. That's the ordinary voltage, but you can also attach one on the top and one on the bottom. And if they're opposite each other, that's the Hall voltage. Without a magnetic field, there wouldn't be any Hall voltage. The current flows in one direction, the voltage drop is that. But if you have a magnetic field on, it tends to force the electrons are moving and they get forced up, and it builds up electrons on one side, and then on the other side, there's less electrons, so you get an electric field perpendicular, and that's the Hall voltage. And that was discovered in 1880 something by Hall. actually. And it happens at room temperature in metals. It's much more pronounced, it turns out, in semiconductors. But it's called the Hall effect, and it's classical and was around for years and years. And usually what happens is, if you have a fixed current and you measure the Hall voltage and you increase the magnetic field, the Hall voltage, or the Hall resistance, which is the voltage divided by the current, just increases linearly. That's more magnetic field, more Hall voltage. But what they found instead was, in this case, it would increase for a while. This is at low temperatures now. They'd increase the magnetic field, and then it suddenly leveled off, and you'd have a whole interval of magnetic field. You might be able to change the magnetic field by, let's say from 2 Tesla, that's Tesla is 10,000 Gauss, so 2 Tesla to 3 Tesla. These are strong magnetic fields, and it would be flat, almost really flat, and then it would go up rather steeply, and then it would flatten out again, and there'd be this series of plateaus in the magnetic field. If you measured the longitudinal resistance in the same interval of magnetic field, these special intervals of magnetic field, they found that the resistance became zero, or at least unmeasurably small. So we have this amazing thing of a flat resistance. And then, even much more amazing, they said, well, okay, what's the value of the resistance on this plateau? And they compared the different plateaus. And what they found was that, let's say, there might be one plateau at 25,850 ohms, and the next one was half of that. And then there was one at a quarter of that, or a third of it. So the plateaus, it turned out that this 25,850 ohms is exactly, it's just Planck's constant divided by the square of the electric field. It's just some combination of fundamental constants. Planck's constant, the fundamental constant of quantum mechanics, divided by the charge of the electron squared. And that has units of a resistance, as it turns out. And that resistance is this 25,000 ohms. And here you had this, and it turned out that in the original measurements, it was flat to like a part in 10 to the 6th. And more recently, it turns out to be part in 10 to the 8th or 9th, if they can measure it. And of course, we believe it's exact, but at the time, it was just surprising. And this was just, it wasn't as though it was a carefully made resistor. It was just the wires were just soldered on. It wasn't particularly rectangular. It was roughly rectangular. It didn't, in different samples, you could look at different samples, different materials, and this kind of universal thing suddenly popped out, which is really rare in solid state. Usually, if you measure the resistance of a piece of steel, let's say, the resistance depends on how long it is, how wide it is. If you put some notch in the material, it'll change the resistance. It's not robust, but here, and it certainly has nothing to do with any fundamental constants. So this was obviously something that was very exciting. And when I heard about it, I didn't see the paper originally, but my attention was called to it. So actually sometime later. And at the same time, I didn't have an explanation for why it was so exact, but there was an explanation that first came out from Bob Laughlin. The plateaus, sort of that there'd be something like a plateau, was kind of predicted, but that it should be flat, and really this perfect was not. And there were very deep reasons for that, and I found that very interesting. And then 2 years later, people working, there were some people from Bell Laboratories, they were working at MIT at the high magnetic field. They found something called the fractional quantized Hall effect. So whereas as the ones I told you about were the integer ones, namely you had resistances which were were this fundamental constant h over e squared, 25,000 ohms, divided by an integer. Now they found plateaus where instead of an integer, it was some rational fraction. First it was 1/3 and 2/3, and then 2/5 and 4/9, mostly odd denominators. And that was completely unexpected. That one, there had been not even any hint of what was going on. And it took more than a year to even begin to understand what was going on there. And there, whereas the original one you could sort of understand in terms of non-interacting electrons, you needed quantum mechanics, and you needed to understand impurities and localization and a lot of subtle things. But at least it was something that you could understand in terms of individual electrons acting collectively, but not with anything really magic about it. But this fractional quantized Hall effect, it was something that was totally unexpected. It required electron interactions in a way, interactions between electrons acting in a way that no one had ever conceived of before. It was really a totally new state of matter at the electronic level, a totally new thing that only could occur in quantum mechanics, only occur with strongly interacting electrons. And then it turned out that there were many different kinds of fractional quantum Hall effect. There weren't just one kind, and there were interesting things that happened at the edges, and so it's been enough to keep me interested for the last it's been 40 years actually, almost 1982 is when it was first discovered. New things have double layer systems, and now it's been interesting things that happen in graphene and semiconductors and new materials and so forth. Anyway, that's what it is. It's a little long-winded, but that's what it is.
It's very interesting. A lot of things about that theory were very cool. Is there any advice you have for students aspiring for a career track in your field?
Well, obviously, you need to know a lot of math if you're going to do theoretical physics, any kind of physics. If you're going to do experimental physics, you better understand the theory pretty well also. And by the way, when I say theoretical versus experiment, I'm not talking about practical or pure. I'm talking about as a theorist, I don't actually have a laboratory. I work with people who do have laboratories and do experiments. They may be doing experiments very pure, very materials that are far from applications, or they may be applied, and they're theorists who do applied things too. But in any case, if you're going to do any kind of physics, you need to know, you have to be good in math, and you have to like math. You better like it and enjoy it, and you should be curious about the world around you and want to find out about it. If you want to do experimental physics, you better be pretty good with your hands and like to fix things that get broken, because things get broken in the laboratory. Actually, they get broken in theory too sometimes, but you have to be able to solve puzzles. You have to like solve puzzles and try to fix things that seem to be broken.
Yeah.
So one other thing that I think is important and sometimes is neglected by science students is that it is really important to develop communication skills of various kinds. You have to be able to write well, clearly explain things that are hard to explain, but also write grammatically and write in a way that people can enjoy reading it. And you have to be able to speak as well, give talks. You have to learn to understand what's important and what's not, and how to communicate ideas that are complicated to try to simplify them. Of course, none of us really succeed in this completely. You're only doing the best you can, but I think developing those skills, even starting at an early age, is important.
So would you be willing to have high school students reach out to you, or is it okay if high school students contact you for advice and guidance via email?
Sure, absolutely.
Okay, well, thank you so much for your time.
You have my email, and you may pass it on to your friends.
Yeah, yes. So that was Bertrand Halperin. And check out our website for additional resources to learn more about him and his field.
Thank you, and we'll be back with another episode.